Have you ever heard of the Venturi Effect? If you're a gearhead or a mechanical engineer, then you almost certainly have, because it's the working principle of a carburetor. The Venturi Effect states that a fluid's velocity will increase and its pressure will decrease as it flows through a constriction in a channel, like the one behind me here. If you're like me, that seems really counterintuitive and wrong. I'm here to give you, but really mostly me, an intuitive understanding of why the heck that happens. I'm JT, and this is Over-Engineered. This slow-mo footage of a carburetor, which comes from the SmarterEveryDay YouTube channel that I've linked below, is a perfect example of what a Venturi is and what it does. The carburetor makes use of this effect to suck fuel into a high-speed, turbulent airstream that turns it into tiny droplets for efficient combustion. Modern fuel injectors of all sorts, from Otto-cycle engines to gas turbines and rocket engines, use some sort of constriction to boost fuel flow velocity and reduce output pressure to aid in atomization of liquid fuels. Venturi nozzles are found at gas pumps, where they enable the handle to automatically shut off the flow of gasoline when the tank is full. Bunsen burners from your high school chemistry class use the Venturi effect to draw more air into the flame so it burns hotter. They're used in wind tunnels to increase flow speed and modify the Reynolds number of the flow for aerodynamic testing. Another particularly cool example is the underbody diffuser found on F1 cars, which makes use of the Venturi effect to suck the car onto the road surface with great force, increasing traction. Examples are fun, but why is the Venturi effect called that? It's named after this absolute unit, Giovanni Battista Venturi, born in 1746. However, the phenomenon is represented mathematically by Bernoulli's principle, which the even more giga-chad Daniel Bernoulli first recorded in 1738. I'm not sure why it's named after Venturi though, because it's pretty clear from his equation that giga-chad Bernoulli definitely had a better understanding of the relationship between fluid flow speed and pressure 8 years before Venturi was even born. Based on his Wikipedia page, it seems like Venturi was a skilled political operator, and he apparently appointed himself the historian of his city after the old historian died. I'm betting Venturi massaged the history books a little bit to make it look like he did more than he really did. But enough about old rich dudes. At a cursory level, it seems totally backwards that the pressure would drop where the flow is constricted, right? If we shove a bunch of fluid particles into a constriction at high speed, then they need to be redirected inwards in order to get through. And I would think that the process of redirecting those particles would result in them bouncing off the walls with more force, more energy, more pressure. It seems like a decent explanation, but it's a fallacy, and especially in the case of subsonic flow. You can get the accounting right in your head if you look at it from an energy perspective instead of pure mechanics, which was Bernoulli's insight with his famous equation. It's really just an energy balance equation that needs to stay constant because of the first law of thermodynamics. The energy that comes from the pressure combined with the energy coming from the speed must always be the same, but the fluid can trade one for the other. That's exactly what happens in the constriction, as pressure energy is traded for kinetic energy or flow speed. This necessarily means that pressure must drop when flow speed increases to make sure the energy is constant. That explanation is good enough for most, and it makes mathematical sense, but it's still not mechanically intuitive. I wanted more, and I wasted days of my life mulling this problem over, so I decided to make a simulation to prove to myself what's going on physically with the fluid particles that makes this possible. And that must mean it's time for a coding montage. What you're looking at is a 2D simulation of an ideal monatomic gas inside of a channel that is essentially modeled as a wind tunnel with a constriction. The tunnel connects to itself virtually through the vertical sidewalls, which are not actually walls. When a particle reaches a vertical boundary, it just reappears with the same speed on the other side of the boundary as if the two ends were wrapped around and connected at the back side. The visible portion of the simulation is smaller than the full simulation, which has extra length in the wide section that isn't visualized on the display. I designed it like this because it's the simplest method I could think of to model the back pressure of the slower moving fluid past the constriction, which is absolutely critical in demonstrating the Venturi effect. Without that back pressure, you don't have a Venturi. You have a rocket nozzle blowing gas into a vacuum. The gas particles in the sim all start with random positions and speeds and can collide with each other elastically, meaning energy, which is directly proportional to squared particle speed for a monatomic gas, is conserved. That's what makes a gas ideal. I figured I could just give all the molecules an initial push and they would continue to flow forever because this is an ideal simulation with no heat loss and theoretically no entropy generation. I was wrong. The second law of thermodynamics is a bitch and it comes for everything. Even idealized simulations. Entropy always increases, and systems tend towards random disorder. That's the second law in a nutshell. My best guess about what's producing this entropy is the quantization error of using floating point numbers to store system state, coupled with my approach to dealing with particle overlap, which I call de-overlapping. Those effects add enough randomization that the entropy in the simulation increases faster than you'd think. This means that kicking all the particles once and letting them fly pretty quickly leads to a stationary simulation where the particles have no discernible average bulk velocity, just more random speed than before. Incidentally, that random speed is the definition of temperature. Temperature being the average kinetic energy per molecule of a gas, and kinetic energy is a half mv squared. So speed, temperature equivalents. I iterated my code several times trying to solve the entropy problem and get the particles moving consistently. I ultimately decided that the best approach was to emulate a real wind tunnel as closely as I could. This meant inserting a fan that gives the particles a swift kick in the ass as they pass through. Doing that made the particles speed up forever though, and my simulation reached ludicrous speed, which broke it. I failed to account for the constant energy input of continuously adding speed to those particles because I'm stupid. Real wind tunnels, many of which push megawatts of power into their blowers, must bleed heat energy to prevent this issue, which they do either through the walls or with intentional heat exchangers to remove heat from the air inside. You can see that in this aerial view of the wind tunnel at MIT on Google Maps. The blower here is followed directly by a heat exchanger right here, and you can see the plumbing that pulls the heat away. I removed the extra energy through the walls in my sim by sapping a bit of speed from each particle wall collision. I used a proportional controller to set the heat loss rate and maintain total energy in the simulation. Something to note about the Venturi effect with air is that the relative pressure differences are pretty small at normal speeds. Absolute pressure at sea level is around 100,000 pascals, so you need a high speed in meters per second to observe a significant pressure drop on an absolute graph like the one at the bottom. My sim isn't using any real units, but it displays a similar effect, and I had to bring the flow speed up to Mach 0.7 to highlight the pressure drop and make the molecular effects easy to see. If this were sea level air, Mach 0.7 would be about 540 miles an hour. Another effect of going this fast is that Bernoulli's equation starts to break down. For a gas, it's more like the pirate code anyway.
The code is more what you'd call guidelines than actual rules.
I'll explain this further in part 2 of this video. The graphs on the bottom are computed numerically by splitting the visible portions of the graph into chunks and taking measurements of the particles in those chunks. Density in 2 dimensions is the number of particles over the chunk area. Average horizontal speed is self-explanatory. Temperature is a bit more complex, as you'll recall that it's the average random energy per particle, so we need to subtract the bulk average speed component from each particle's x velocity before computing the energy as the sum of the x and y speeds squared. If we don't do that, we'd be quantifying stagnation temperature, which is more like a total energy metric for the moving fluid. Please note that all those graphs at the bottom only show relative measurements, and their y-axes have no physical units. The x-axis is distance along the channel, and the colored lines show relative changes for each measurement along the channel. If you wanted physically meaningful quantities on each of these numbers, you'd have to do a lot of accounting and calibrating to find the constants that define this virtual gas. That'd include specific heat values, particle mass, gas constant, etc. I didn't feel like doing that, and it'd be boring anyway. I've used 2 methods to compute the pressure to sanity check my simulation and prove that it obeys the ideal gas law. The first method is to keep a running tally of the total amount of momentum transferred to the walls by adding the perpendicular components of the velocities on each wall bounce. With some constant scaling factors, this sum of momentum differences will be proportional to the pressure, and that's enough for a relative measurement. The second method for determining pressure comes from the ideal gas law itself. By rearranging the terms in PHET, it's clear that the gas pressure must be proportional to its density multiplied by its temperature, 2 quantities that have already been computed. As you can see in the graph, the two methods of tracking pressure agree with each other pretty well, with the caveat that the momentum method has more noise. The last thing I graphed is the Mach number, which is just the ratio of the flow speed in each section to the local speed of sound in that section. I did bother to calibrate this parameter, so what you see is not a relative measurement, it's the actual Mach number of the simulated flow. I'm going to talk about Mach number and the speed of sound a lot more in part 2 of this video, but for now all you need to know is that the Mach number, when lower than 1, tracks pretty closely to the average relative speed, and the Venturi effect is generally valid in this subsonic regime. Alright, now I have a working 2D particle simulation of an ideal gas flowing around a wind tunnel with a constriction in it, and I can independently use the fan to modify the flow speed in order to get the result that I want. So let's get back to the original question and explain the Venturi effect from a pure momentum perspective by observing the molecules more directly. Looking at fluids this way has a particular name. Scientists call it the molecular kinetic theory of gases. The color of the molecules in the visualization right now shows their average pressure in that local section, with blue being low pressure and red being high pressure. The graphs show the pressure dropping where the speed is high in the constriction, as we'd expect. This is the Venturi effect in action, the exchange of random particle motion and pressure for unified particle motion and flow speed. It's easiest to develop an intuition for how the momentum changes by working backwards. To visualize this solution, you need to have a good understanding of the difference between the bulk average speed of the particles together and the average absolute speed of each individual particle. The average absolute speed in the stationary reference frame is roughly the same across the whole channel, which is to say that each particle moves roughly as fast as every other particle. What we quantify as flow velocity is more of a measure of motion uniformity than an actual increase in the speeds of the individual particles. When they move in the same direction instead of randomly, their bulk average speed is higher because there are a lot fewer particles moving against the stream, so to speak. If we accept that the flow speed must be faster in the channel because of the decreased flow area, the intuition for the lost pressure becomes much clearer. Working from the left, we can see how the slow-moving and more random fluid presents a block for the faster-moving fluid exiting the constriction. When the particles strike this slow-moving and more random fluid, their momentum spreads out, and thus more of it is translated to the walls as pressure. The gas temperature has increased as well, which is obvious if we remember that temperature is a measure of the amount of random kinetic energy in a fluid. If I show you the fluid in the constriction from a frame of reference moving at the fluid's bulk average speed, you can see how much slower all the molecules appear to be when compared to the particles in the wide sections. This is a pure visual demonstration of reduced temperature. So what about the channel entrance? Working backwards with our same intuition here, we see that the bulk average flow is fast in the channel, meaning the individual particles are collectively speeding away from the oncoming ones faster and faster as the channel constricts. This relieves back pressure on the incoming flow, so the randomly moving particles from the wider region vent into the narrower, reduced back pressure zone. The molecules lose some of their randomness as they collectively rush to fill in the vacancies left by the escaping particles before. Again, their absolute speeds don't change much, which you can see by tracking any individual particle, but they move together with less bouncing and randomness, less temperature, less bouncing, and therefore less pressure in the high-speed narrow region. People often say pressure gradients drive flow, and this is the mechanism by which that happens in the fluid, as the stored random energy wants to escape into areas with less back pressure. This similar situation shows the effect when particles escape into a pure vacuum. It's easy to notice how the molecules move in one general direction after exiting at high bulk average speed. The constricting zone does this same thing to a lesser extent by relieving the back pressure through increased speed, thus acting as a momentum concentrator, redirecting randomness into uniformity, exchanging random particle velocities for uniform linear particle velocities. Stated another way, the particles gain horizontal speed by losing vertical speed. This exchange means that the particles bounce off the walls with glancing blows and less momentum transfer than in the wider channel regions, decreasing pressure. Explaining the Venturi effect is always a bit of a catch-22, as you almost have to accept it exists to explain its existence. The real key takeaway here is that random particle momentum is concentrated when the channel constricts to become cooler, uniform, and linear. The gas molecules trade temperature for linear speed. Then the momentum flux spreads out as the channel expands to become hotter and more random again. The more random the motion, the higher the pressure if all else is equal, because the particles bounce off the walls at higher angles and transfer more momentum that way. This is also shown in the ideal gas law because pressure is proportional to temperature, so dropping that temperature will reduce pressure. The particles have about the same individual speeds everywhere, so the total energy is about the same everywhere, and you merely exchange randomness for linear motion. It's kind of like a heat engine in that way, which is a perfect segue to the next video where I'll discuss what happens when we aggressively increase the flow speed in the channel. Spoiler alert, that's how rocket engines work, so get excited. It's shockingly cool. That was a terrible joke that you'll hate me for when you see what happens to the exhaust temperature of a rocket nozzle. It gets cooler when it leaves. Also, shockwaves are fun. Anyway, that's my intuition for the Venturi effect, and I hope you enjoyed it. Thinking about fluids this way can be a bit more difficult, but it really helps you to get under the hood and predict some of those counterintuitive effects that fluid dynamics is famous for. Leave a like or a comment if you enjoyed this video or found it helpful. Consider subscribing. Have a good one.